Welcome back to our deep dive into software design essentials. Today, we're exploring um, the fundamental ideas behind designing a rate limiter. Think of it as the unsung hero of high scale systems.
I'm excited to get into this. So, rate limiters, right? They sort of act as the traffic controllers for all those endless API requests.
Exactly. A rate limiter is basically a mechanism to control how many requests a client or service can send over a specific time period. It's um, like having a bouncer at a club who checks each request before it enters the
I
system.
get that.
It helps keep everything running smoothly, preventing overloads and even deterring DOS attacks.
That makes a lot of sense. It's not just about stopping abuse, but also about ensuring your infrastructure isn't overwhelmed and keeps operating efficiently, right?
Absolutely. In fact, by capping, say, 2 posts per second from a user or limiting how many accounts an IP can create in a day, you not only protect your servers from being bombarded, but also reduce
Right.
unnecessary processing costs. It's a way to keep both performance and budget in check.
Now, when we talk design, what key requirements do you think should be on everyone's checklist when architecting a rate limiter?
There are several critical factors. First, accuracy. It must enforce the limit exactly so no rogue request slips through. Then, low latency is essential because every extra millisecond can add up. Also, memory efficiency matters, especially because many systems use in-memory stores like Redis. Additionally, you need it to work seamlessly in distributed environments, which is crucial for handling high-volume traffic. And of course, handling exceptions properly with clear feedback like HTTP 429 errors.
Yep, those headers really help. I see. So it kind of means the limiter has to be both precise and lightning fast, all while being cost effective. That sounds like a tall order.
It sure is, and it's like tuning a delicate instrument. You adjust things just right, and even a small misconfiguration can mean too strict or too lenient limits. Every detail has to be balanced just perfectly.
Exactly. Now let's shift gears to where this rate limiter is positioned in the overall system. Some people might think about client side implementations. What's your take on that?
While you can do client-side rate limiting, it's generally not reliable because clients can manipulate those limits. The best practice is to enforce it on the server side, often as middleware or within an API gateway. This centralized control ensures uniform application across all incoming requests.
Yeah, that centralized approach really simplifies management. So by having it at the gateway or server level, you not only get consistency but also add an extra layer of defense, right?
Exactly, it's an all-in-one package. Traffic shaping, authentication, and even SSL termination can be handled together, ensuring a robust defensive architecture.
All right, let's get into the nitty gritty. There are several algorithms for rate limiting. Can you walk through some of those?
Sure thing. One common approach is the token bucket algorithm. Picture it like a bucket that gets filled with tokens at a constant rate, and each request takes one token. If your bucket's empty, the request gets dropped. It's great for handling bursts, but you have to be careful tuning the bucket size and refill rate.
Adjusting those parameters is key. What about the leaking bucket algorithm?
With the leaking bucket, think of it as a fixed size queue where incoming requests get processed at a consistent, steady pace. If the queue is full, any new requests are simply dropped. It provides a predictable outflow, which is excellent for maintaining consistency.
True, but doesn't that sometimes drop valid requests during high bursts? Right, and that leads us to the fixed window counter, doesn't it?
Yes, exactly. In the fixed window counter, time is divided into intervals, and once the counter hits the limit for that window, further requests are blocked until you reset. It's super simple and memory light, but it can sometimes allow a burst of requests at the edges of the window.
That edge case can be a bit iffy. Now, I've heard about something called the sliding window log. How does that differ?
The sliding window log is a bit more granular. It keeps a log of each request's timestamp, then counts only the requests within the current rolling window. It's very accurate, but it comes at the cost of increased memory usage because you're storing all those timestamps.
Right, so you get precision but might need to trade off on memory. And then there's the sliding window counter, correct?
Exactly. This method blends the fixed and sliding window approaches. It uses counters for the current and previous windows to give an approximate rolling count. It smooths out traffic spikes without the heavy memory footprint of the sliding window
Yeah,
log.
I like that balance. But just to respectfully challenge one point, don't some argue that the sliding window log's precision is worth the extra memory cost, especially in systems where every request matters?
That's a fair critique. In environments with very precise requirements, the extra memory might be justified. However, in a high traffic cost sensitive system, the sliding window counter might offer a more pragmatic, balanced solution.
That makes sense. Moving on, let's talk about distributed environments. How do you handle rate limiting in multi-server architectures?
In a distributed setup, things like race conditions and synchronization challenges become very real. Imagine multiple servers trying to update a shared counter in Redis simultaneously. Without atomic operations, like those provided by Lua scripts, things can go haywire.
Right? Atomicity is crucial. And it sounds like centralizing the data store with something like Redis is essential here, correct?
Absolutely, centralizing through Redis helps ensure that every instance of the rate limiter has the same up-to-date picture. Otherwise, you might have one server think a client is under the limit while another disagrees.
Yep, consistency is everything. Now, what happens when a client goes over their limit? How does the system handle that?
When clients exceed the limit, the system typically returns an HTTP 429 status code, which means too many requests. But it doesn't stop there. The response usually includes headers like X rate limit remaining, X rate limit, and X rate limit retry after to guide the client on how long to wait before
Right.
retrying.
That detailed feedback is super helpful for automated clients. That kind of detailed communication is so important. It helps clients adapt rather than just getting a confusing error.
Exactly. It's all about transparency with clients so they can implement proper retry logic. It smooths over the potential friction when limits are hit.
And what about performance optimizations? How do you scale a rate limiter to handle high traffic without becoming a bottleneck?
Great question. Performance optimization often involves a multi-data center setup, deploying rate limiter instances near users to minimize latency. There's also the concept of eventual consistency, which ensures responsiveness even if there are slight delays in synchronizing data across distributed systems.
Yeah, that's like having local checkpoints to keep things running fast. I like that. A sort of decentralized finesse, yet keeping the overall consistency through central coordination.
Absolutely. And on top of that, robust monitoring plays a vital role. You need to continuously track how well your rate limiter is performing, whether the rules are too harsh, and if any patterns suggest abuse. This way, you can fine-tune both the limits and the algorithm
That proactive
parameters as
monitoring
needed.
really is the secret sauce. In wrapping up, what are the key takeaways for anyone designing a rate limiter in modern systems?
Well, flexibility is key. Your limiter should support different rules, be it per IP, user ID, or API endpoint. A hybrid approach often works best, combining both hard and soft limits to provide the best user experience while protecting resources. And of course, planning for failure is crucial. Set robust exception handling and monitoring in place.
Mm-hmm. Planning for the unexpected really makes all the difference. That's a solid blueprint. It really shows that designing a rate limiter is as much about art as it is about engineering, finding that sweet balance between precision, performance, and flexibility.
Right, and it's a continuous process. Test, monitor, and iterate to adapt to real world traffic patterns. Every system is dynamic, and your rate limiter must be too.
Well said. This discussion definitely demystifies the intricacies behind rate limiting, and I'm sure it gives many a clear direction when tackling these challenges in their own systems.
For sure. Remember, it's all about ensuring that the infrastructure can handle heavy loads without compromising the user experience or system resilience.
Absolutely.
Keep building those robust systems and always be ready to adjust as traffic and conditions evolve.
Thanks for the insightful breakdown today. This deep dive not only clarifies the fundamental concepts, but also highlights real-world challenges and practical strategies. I know I'm walking away with a lot of new ideas.
Thanks for tuning in, everyone. Let's keep pushing the envelope in software design. Innovate, tinker, and always be prepared for the next challenge. Until next time, keep those systems resilient and those rate limiters sharp.